Usually, which is a bit hard for me to admit, hardware evolves faster than software. So, multiprocessors and multi-core has happened ahead of the concept of parallel programming. When engineers came up with multiprocessor computer systems and multi-core computer systems, this was a challenge facing software developers because software developers were actually had actually to write codes that will benefit from having multiple processors or multiple cores. The challenge was to be able to divide these activities with balance and learn how to split data while actually paying attention to the dependencies between data, where one set of data might be affected by another set of data uh, that is used by a thread running on a different processor. Testing and debugging for codes that are written to run simultaneously on different processors, is a highly challenging task because you don't know. It's very, very hard to predict actually how these threads are going to end because each thread can take several paths because there would be conditions and loops and cases that can, it's really hard to predict which way or the other will this thread be executing. Here we have to distinguish between two major concepts in not only in operating systems, in programming generally, or in computing. These are parallelism and concurrency. When I say parallelism, that means there are multiple threads, multiple programs, multiple processors running at the same time on different CPUs or on different cores. But when I'm talking about concurrency, that means there are multiple processes or multiple threads that are running within the same time, not in the same time. Because concurrency can mean that these processes or these threads are using a single CPU taking turns. So they will look to the user as if they are um, actually being executed in parallel, and that would be just an illusion. It's safe to say all parallel systems are concurrent systems, but not all concurrent systems are actually parallel systems. Parallelism can be divided into two categories. It's either data parallelism, where data is divided between processors or between cores, and computations are run on that data. Let us assume we are, for example, we have huge set of data and we need to calculate regression, for example, okay, for statistics. This can happen with splitting this data between several CPUs or several cores. The same process will be, the same task will be done in parallel to speed up the computation. Okay. While task parallelism, that means there are multiple different tasks assigned to different threads. Each of these threads is running on a separate core or a separate processor. Usually, the system would be using a hybrid form of this, يعني not strictly data parallelism or strictly task parallelism. It would be a hybrid between both, and it totally depends on what tasks are we actually executing. Nowadays, we can talk about hardware threads and where new architectures use new improved type of hardware to support hardware threads, and that is out of our scope in the course. If you want to look into an illustration to distinguish between parallelism and concurrency, we can see that we have actually here uh, multiple tasks from T1 to T4. In concurrency, they will be taking turns running on a single CPU. That will make the user feel that these tasks are actually running concurrently at the same time on that CPU. Because the CPU time is very short, much shorter than our time as human beings. While in parallelism, they will actually be running on two separate CPUs or separate cores, and actually being executing at the same time, as you can see in the illustration. A process can be what we call a heavyweight process. That is a process with an only single thread of execution. Or a lightweight process, and that is a process with multiple threads of execution. You can see the difference that will show you clearly how having multiple threads is much efficient and provides economy. For a process to be created, it needs a stack, it needs register, it needs its code section, its data section, and the files it's using. That means it actually the space in the memory that is assigned to it. While threads share the code section, the data section, and the open files, each one of the threads had its own register set and stack. That minimized the amount of resources needed to create a thread. Threads can be implemented in user space, and those are called user threads, or in kernel space, and these are called kernel threads. User threads are usually completely managed by the applications. And a good example for user threads are the threads libraries such as pthreads or Windows threads or Java threads. While kernel threads are supported by the operating system. And almost all operating systems I know support kernel threads. Windows, Solaris, Linux, Unix, Mac OS, all of them support kernel threads because it provides more efficiency, more responsiveness, better utilization for resources, economy, all the things we've said. The relation between user threads and kernel threads can be implemented in one of three ways. It's either many-to-one, or one-to-one, or many-to-many. Many-to-one, that means many user threads are actually mapped to one kernel thread. And this is implemented in Solaris Green Threads. This is a very early version of Solaris. And in all GNU portable threads. This model is rather inefficient because although in the user space there are multiple threads, mapping them into one kernel thread makes multi-threading almost not useful. Imagine one of these threads has performed a blocking request. So the kernel thread will be blocked and all other threads, user threads, will be also blocked until the blocking request is done. That's why this wasn't a very popular model, and it was replaced by the one-to-one model, where every user thread has a kernel thread that is mapped to. This is definitely a very efficient, a highly responsive model, but we have to be very careful implementing this. We don't want to overwhelm the system with too many kernel threads, because kernel threads are still costly to create and manage. Yet, this model is actually adopted by almost all now existing operating systems. Windows, Linux, and Solaris 9 and later, all of them uses one-to-one thread model. Earlier versions of Solaris use this really very interesting and it's my favorite actually model, which is many-to-many, where multiple user threads are multiplexed to multiple kernel threads. Kernel threads can be of a fewer number than user threads, and they were an intermediate level process that is called a lightweight process, used to be as a multiplexer. So when I give 10 user level threads, so I need 3 kernel level threads, the 10 user level threads will be multiplexed into these 3 kernel level threads, and that is efficient, and it saves resources, and at the same time it gives us the full benefits of multi-threading. As been saying, so in many-to-many in Solaris, they had this intermediate process, over this with two-level threading. This intermediate process, the lightweight process, was the multiplexer, and that was, I don't know why they stopped doing this. I have no idea. I wish I can ask them. And US Solaris uses the one-to-one model. It's actually, one-to-one model is easier to implement and it's straightforward rather than this. But this was an awesome design idea. I love the design. Threads can be